Hello, good morning students. Today I am going to cover a syllabus on BSc 5th semester real analysis in which Unit 1 Riemann integration. I am Dr. Krishna B. Chavareddy, Government First Grade College, Naragon. So before going to discuss about Riemann integration, first I should start with some basic definition of upper and lower Riemann sums. Let f be a bounded real valued function which defined on a closed interval ab and p be any partition of that closed interval ab. Then we define the supremum and infimum like this. Small mr is the greatest lower bound of f of x for all x belongs to the subinterval, and capital Mr is the that is LUB least upper bound of f of x for all x belongs to the subinterval xr minus 1 comma xr. Then we can define that is the LP of f is equal to the summation of small mr delta r, where r is running from 1 to n, which is called the lower Riemann sum or lower Darbach sum. Simply we can say that lower sum of f on closed interval with respect to any partition p. Similarly, we can define the UP of f, that is as summation of capital Mr delta r, where r is running from 1 to n, which is called the upper Riemann sum or upper Darbach sum. Simply we can say that upper sum of f with respect to any partition p then. And next we would like to start with some properties of Darbach sums or Riemann sum. Let us see first property. The statement of this property is let f be a bounded function in the closed interval ab, and let small m and capital M be infimum and supremum of that f on closed interval ab. Then for any division or partition p of closed interval ab, then we have a relation is upper sum is always less than or equal to the lower sum is always less than or equal to the upper sum, and this also relation with that is the m of b minus a and capital M of b minus a. Also which can be stated as let f be a bounded and real and p be any partition of closed interval ab. Then we have proved this relation, and let us see the proof of this property there. Let p be any partition of closed interval ab, since f is bounded on closed interval ab. So f is bounded on each of the subinterval xr minus 1 comma xr, where r is running from 1 to n. Let capital M and small m be the supremum and infimum of f on closed interval xr minus 1 comma xr. Then for every value of r, we have a relation is always infimum should be less than or equal to the supremum, in which also that is the mr should be less than or equal to capital Mr, and taking delta r throughout there, and also this relation plugged into summation there, and finally we can have that is a relation with that is m of b minus a, because where summation of delta r is the length of the subinterval, that is b minus a, and then here we have that is LP of f less than or equal to the UP of f. We have this relation. And next property is let f be a bounded function and p is any partition of closed interval ab. Then lower sum is also less than or equal to the upper sum. Let f be a bounded and p be a partition, and since f is bounded in each of the subinterval xr minus 1 comma xr, and let small mr and capital Mr be infimum and supremum of f on closed interval xr minus 1 comma xr, which is subinterval. Then for every value of r, we have this relation, as we know that just taking a delta r throughout there, plug into summation where delta, as we know that this definition of these LP of f and UP of f, making use of those definitions, we have that lower sum is always less than or equal to the upper sum. And third property of this Riemann sums, let f be a bounded function on the closed interval ab, and p and p star be partitions of closed interval ab, such that p star contained in p, that is p star is a requirement of p. Then we have a relation here. Lower sum of negative function is always equal to negative of the upper sum, and second one, upper sum of negative function is also negative of the lower sum. And also we have a relation there LP of f is less than or equal to the LP star f, and UP of f is greater than or equal to the UP star of f. Let us see the proof of this. Let P and P star be any partition of that P closed interval AB, where P star is refinement of P because it contains an additional point xi such that xi lies between the subinterval xr minus 1 comma xr, and let capital MR and small mr are the supremum and infimum of f on subinterval. Then we can make use of the definition of lower sums, that is LP of minus f equal to summation of minus mr delta r, and taking minus outside, then it arrive at the negative of the lower sum is equal to minus of, that is the upper sum. And also make use of the definition of upper sum is also we have that relation, just we have that summation of minus mr delta r, and taking negative outside, then it arrive at the upper sum of negative function is also equal to minus of, that is the lower sum. And third relation here, let small mr prime, small mr double prime and mr be the infimum of f in the intervals, that is xr minus 1 comma xi to xr and xr minus 1 comma xr. Then we have that relation, as we know that mr should be less than or equal to the mr prime and small mr should be less than or equal to the mr double prime. Since the contribution to a lower sum and LP star of f of each of the subinterval except this subinterval xr minus 1 comma xr is the same. Now contribution of the subinterval xr minus 1 comma xr e to LP of f is, that is the mr into xr minus 1. Since the subinterval xr minus 1 comma xr is splitted into two subintervals xr minus 1 to xi and xi to xr, it follows that the contribution of subinterval xr minus 1 comma xr to LP star of f is, that is the mr prime into xi minus xr minus 1 plus mr double prime into xr minus xi. Hence we have that is LP star of f minus LP of f, that we have a relations, just we can substitute all those relations here. Finally we can have that relation with LP star of f minus LP of f, which is always greater than or equal to 0, as we have that is relations in that. So that hence we have arrived at that LP star of f is greater than or equal to LP of f, or LP of f should be less than or equal to LP star of f. We have discussed this case when P star contains exactly one point more than P. If P star contains more than one point, that is P points, so then we have repeating the same argument P times, we can prove that LP of f should be less than or equal to the LP star of f. Similarly, we can prove that exactly as we have seen in the third relation, so that we arrive at, that is the UP of f should be greater than or equal to UP star of f. Then we have a fourth property. If f of f, e, p, f and g are bounded functions and p is partition of AB, then upper sum of f plus g is less than or equal to the upper sum of f plus upper sum of g. And second one, lower sum of f plus g is greater than or equal to the lower sum of f plus lower sum of g. And third relation, oscillatory sum of f plus g is less than or equal to the oscillatory sum of f plus oscillatory sum of p comma g. Then. And we have a proof of this here. Let f and g be bounded functions on subinterval closed interval AB. Let p be any partition of AB, and f and g are bounded on closed interval AB. Then it implies f plus g are bounded on closed interval AB. Let us we assume that mr prime, capital MR prime and small mr prime be the supremum and infimum of f on subinterval xr minus 1 comma xr, and mr double prime and small mr double prime be the supremum and infimum of g on subinterval xr minus 1 comma xr. Then we have mr and mr be the supremum and infimum of f plus g on that. We have that first relation is here capital MR prime and capital MR double prime are supremum of f and g on the subinterval. Then we have a relation f of x should be less than or equal to MR prime, and g of x is also less than or equal to MR double prime for all x belongs to subinterval IR, and sum of these two also less than or equal to MR double prime and MR prime for all x belongs to subinterval. Then just taking that is f plus g with x less than or equal to that MR prime plus MR double prime for all x. That hence MR prime and MR double prime is an upper bound of f plus g on the subinterval, but capital MR is least upper bound of f plus g on the subinterval. So we have that is capital MR should be less than or equal to the MR prime plus MR double prime, and taking a delta throughout that, and finally we have arrive at this is capital MR is f plus g, so that up of f plus g upper sum of two functions f plus g is less than or equal to upper sum of f plus upper sum of g. And also we have a second relation, small MR prime and MR prime are infimum of f and g on subinterval IR, here in which fx should be less than or equal to small MR prime, g of x should be less than or equal to, greater than or equal to MR double prime for all x should be belongs to that is the subinterval. Then we can sum of these two f of x plus g of x, and also we have that relation here, and then we can have for all x belongs to IR there. Then f plus g greater than or equal to this, and but MR prime plus MR double prime is the lower bound of f plus g on this subinterval. Therefore, this relation is small mr should be always greater than or equal to the small mr prime plus small mr double prime. Just taking a delta r and taking plugged into summation there, and we arrive at lower sum of two functions f plus g is greater than or equal to the lower sum of f plus lower sum of g. And also similarly we can prove that relation here, upper sum of f plus g is equal to upper sum of f plus g minus LP of f plus g. Just we can have some relations, just we can make use of that relations. We have arrived at that is the oscillatory sum of two functions is less than or equal to the oscillatory sum function of f plus oscillatory function g. So we have used some references here. So thank you.